Hi everyone, my name is Az Balabanian, and today I'm going to be talking about the science-based decision making in VR and AR. And by science, I mean more specifically like cognitive science and neuroscience, and how you as a developer can really benefit from like understanding some of the basic principles of how your brain works and how that really can incorporate into building better products, and specifically why that is so effective for VR and AR. So, yes, what we'll be talking about today, the basics of how VR and AR work from a cognitive science perspective, examples of how, whoa, we're skipping through this. Come on. Maybe we'll just use good old spacebar. So yeah, examples of how developers have been using cognitive science research to build better products. Even though VR kind of has only been around for the last 2.5 years, at least on the consumer side, we've really seen a lot of iteration on the design side, and we'll be kind of talking about that today, and hopefully you guys can learn on some of their learnings, and how we can use science to predict the future of VR and AR, because that's the stuff that I like as well. We all want to make good predictions. And we'll have a Q&A at the end if we have time. So yeah, I don't think this is working too well. So who am I? I'm this guy with a crazy rig. I like VR headsets. I like cameras. I'm a cinematographer and a DP, and I shoot a lot of commercials and trailers for specifically with VR companies and AR companies, because there's a lot of very specific marketing needs that come with VR. There's these challenges of like, how do you actually market VR to people that know nothing about it? It's quite a big challenge, and even big companies with tons of budget have a very hard time doing that. So I try to help in that regard. So this is one of the examples of what I mean by like VR trailers and mixed reality trailers. I shoot things in green screens with the player actually in the environment, where you can actually see exactly what they're doing and how they're interacting with the environment. It serves a really nice purpose. Second, I work a lot with photogrammetry and volumetric data, and so I started something called like Everyday Scan, and these are environments that you can actually explore in VR by actually walking around in it. These are 3D scans of real places, and this is me walking around in a VR environment with a virtual camera and shooting this. I'm just kind of showing you examples, and if you like this, actually, I have another talk later today, I think at 4 p.m., where I'm talking much more about this technology specifically and how I think this is going to be a big future medium coming ahead. But more importantly for today, I'm here kind of as the host of the Research VR podcast, which I've been hosting for the last 2.5 years, which is all about the science and design of virtual reality. Like where this is something that I started back when I was in college with actually Peter over here, and we have one more person, 3 cognitive scientists that loved to learn about brains and loved to integrate it with virtual reality. And we realized that a ton of developers don't really know much about brain sciences, and we're like, okay, let's just take these principles, break them down, and apply it to this new industry. So yeah, we talk every week. We have an interview and a podcast with like developers, where we basically bring in people that are smarter than us so that they can tell us what they have learned over the last few years building their product. So in turn, basically this talk is going to be a summary of what we have learned over the last 2.5 years by talking to these developers. So we've had a bunch of people from all these cool companies actually come on and talk about it. A lot of scientists, designers. So why does science matter? VR is hard. VR is definitely hard. It's a new industry. It has a lot of it has very high requirements for it to even work. So things like display technology has to be reinvented for your eyes, right? For it to actually work physiologically correctly for your eyes. You have compute and rendering challenges, because these display technologies need to run at a very high frame rate, and I mean, we'll get into the details of it. We have things like locomotion problems and motion sickness, right? Like how do you move in virtual reality? Is it the same as a video game that you play on a TV? Turns out it's kind of not, but there's some fun things we'll learn about that. Input methods, how do you actually control things in VR? Is it with your hands? Is it with a controller? Is it with your eyes? Turns out the answer is all 3 of those as well. Ergonomics and content. So clearly there's a lot of challenges for VR, and the main argument I'm going to be making today is that cognitive science really provides a big advantage in designing and building software and hardware in VR and AR, and that it can actually help you prioritize which challenges to solve first, and how to get around to it. I mean, as developers, you have limited resources and limited time to spend on fixing these problems, and so you should really try to learn as much as you can from already what exists out there. So yeah, I'm going to be talking about some of these examples that the developers have taught us over the last 3 years. So let's start with motion sickness. We're going to kind of stick to two of the main challenges, and there's enough depth in each that really there's a lot that we can learn. And hopefully, actually before we even go into it, how many people here have tried virtual reality or augmented reality? Nice. Ooh, this is a great crowd. And how many people have developed for virtual reality and augmented reality? Fantastic. All right. So there'll be good stuff for everyone here to kind of take home from. So let's talk a little bit about motion sickness. This is a nice little pumpkin throwing up while wearing a VR headset, as you can imagine. So this is the reason why we have motion sickness. Is you can imagine, even if you forget VR, let's forget VR for a second. If you're sitting in a car and you're reading a book, sometimes people get car sick for that reason. You know, they're looking down, they're reading a book. It's a mismatch between what you're seeing, which is that your world is still, you're looking at a very still book, and what your body is feeling, which is, whoa, we're moving, you know, like 100 kilometers an hour. When you have a mismatch of these senses, one of the theories is that your body thinks it's poisoned, and so if it's poisoned, it wants to throw up everything that it's eaten. That's one of the leading theories as to why motion sickness happens, and VR has that problem as well, where if you're moving fast in a VR environment with a headset on, all your eyes are seeing is that you're moving very quickly, but your body doesn't feel like it's moving. It's kind of the reverse of the car sickness problem, right? Your eyes in the car feel like you're not moving, but your body feels like it's moving. So, but both lead to the same symptom, which is, you know, body sickness. So traditional joystick locomotion, which is what you have with a video game, right? You press forward on a joystick and you go forward. That can cause a lot of motion sickness, and it gives a big headache to developers. Because developers, you know, they've been promised that virtual reality is this huge new medium where you can throw your players into the world, into the game world that they know and love so much. So how are they going to build a game? How are they going to put their main loyal fan base in their game if they can't even move the same way that they're used to, right? If you play Halo or you play Quake, you know about that like fast motion that the players love, and you want to have that in VR. So this was the big scare when 2016 was coming around. VR was about to be released for the consumers, and this is kind of what I call like motion sickness hysteria. We've made a lot of advancements since then, and so we're going to go into how you can actually solve some of these problems and create really good experiences. So at the lowest level, what developers did, at least on the hardware side, what Oculus and Valve did, is actually for them to avoid motion sickness, they needed to render everything. Your headset needs to render everything at least 90 frames per second. If you know anything about like TVs or games, that's already a hard challenge, like to hit 30 frames a second, let alone 60 frames a second. 90 is already such a high bar. So one of the most interesting kind of ways that they built a way to actually hit 90 frames a second is something called asynchronous time warp. It's a cool name. Right? Time warp and space warp. What it basically means is that they got clever in terms of like rendering each frame, where if the game was it was not going to hit the 90 frames a second frame rate, then they could predict based on what the previous frame was seeing, what you would be seeing in the next frame, and predict what that translation would look like based on where your head is, how it's moving, and then try to like warp the world, warp the frame that it drew before into the next frame. So this was something that was developed, done by Dan Beeler at Oculus, actually, and probably was one of the bigger advancements in virtual reality. So here you can see the judder that gets created when you have a low frame rate game. This is kind of simulating what a frame rate issue would look like, and the space warp and the time warp really helped at that end. Another form of solution is, especially in 2016, people were really expecting for VR treadmills to become a big thing, where if you're going to be a hardcore VR gamer, you're going to want to have a VR treadmill at home, right? What? So this is my co-host for the podcast, Peter, walking on a fully free locomotion treadmill, and I mean, it's pretty cool, right? I mean, you think maybe you would want to have one of these, but turns out it's big, loud, expensive, and at the end, it's like too complicated in terms of moving in a virtual environment for it to really be integrated. I mean, you might go to a VR arcade today and maybe try one of these, but you wouldn't really want to buy it at home. And plus, think about it this way, like if we're building virtual reality, we don't need to fully recreate what you do in the real world, right? Like if I want to walk in a video game, I don't actually want to be walking, let's say. Or if I want to travel, 100 kilometers in the video game, I don't really want to walk the 100 kilometers. There should be better ways of doing that. So another way is, this is a locomotion method kind of called walkie, or like running in place. And it takes advantage of how you already are, when you run and walk, you have your arms swinging. The way, as you can see here, is you're swinging your arms in whichever direction, and that's the direction that you move. That was a teabag from the player. It's kind of like grabbing the world and letting go. And turns out your body actually doesn't really get motion sick because you have enough like physiologically like one-to-one in terms of like how your body would be moving. And so it's a clever trick for not getting motion sick and still keeping to the traditional movement that we all know, which is smooth locomotion. This is a method actually is straight from research. So this is from Rask 2001 paper. It's called redirected walking, and it takes advantage of the fact that if you close your eyes and you start walking straight ahead, you think you're walking straight ahead, but you're actually going to be walking in a circle, like a wide swinging circle. It's because you don't really have, your eyes are really the best way you can do some pathfinding and navigation. So it takes advantage of that specific illusion, and what we're seeing here is, on the bottom left is what you're looking at in VR, and that's their movement throughout the virtual space. But what the researchers are actually doing is pretty clever. This bottom square here is the player actually moving in the room, in the real life room, and they're making him move back and forth. But every time he goes and touches the wall, and when he's doing the turn, virtually they're flipping the room by, I guess, 90 degrees in a virtual sense, but in the real world, he's flipping 180 degrees. So the player is actually just moving back and forth without realizing that they're moving in the same exact line. And in the virtual world, you feel like you're moving through a much bigger space. So it's an interesting solution that has come from research, but also what we're realizing is it's very limited. You have to be super like case specific for it to work. If you've ever been to like a VR arcade like the Void, they've implemented something like this, but that's because they have full control over the environment and what the experience is going to look like. And it's not a very good like all-around solution. So this is probably the most popular one that's implemented in games, especially back in 2016. It's called teleportation. It's about raycasting kind of an arc into the environment, and then when you let go, you pop out over there. And so this is how most developers thought you would be solving motion sickness, by not actually moving fast in a virtual environment. Is just like by blink teleporting places and not worrying about the real movement. It's a decent solution. However, my main problem with it is that you don't actually develop a coherent like mental map, like a cognitive map of the space, because for your brain to really like map out a space, you need smooth motion. Like when I'm walking left and right here, I'm seeing parallax in my vision, and I can really understand where people are and where the things are in the room. If I'm just blink teleporting, if you're kind of disoriented, as to where you are. So it's a method, but it's not perfect. So now in 2018, we've had 2.5 years of games and apps that have come out. We've learned some good things. So I'm going to give you some really good examples with the games that have implemented some of these research principles and that have achieved really good locomotion and games that feel good. So this is a clever method called the cockpit effect. And so the game is Vox Machinae, which is a mech game. You're sitting inside of a cockpit and you're flying this huge mech around the room. So the cockpit effect is basically if you put the player inside of a cockpit with kind of thick reference points, like you see the seams of the the pillars, the A pillars and the B pillars, it turns out that actually gives you a reference point that your brain feels like the world is moving around you, but you yourself are kind of in a grounded state. So it really reduces motion sickness. A second method that really has been effective is adding speed streaks. So this is a very high, fast-paced game, right? The guy is flying at God knows how fast, but the faster he's going, the thicker these streaks come on. And turns out, like, having these sorts of visual cues that you're moving in a direction in a quick speed really also reduces motion sickness. Third is, this is straight from a paper, I think back in like 2012 or something, Peter. So it's by adding a nose in the game, like a nose in the rendering. So if you notice over here, this bottom right corner over the IGN logo, there's this nose kind of rendering. It's something you actually don't perceive at all in the game, but turns out it like reduces motion sickness by 10 to 20%. It's pretty clever, and this game has all these different kind of locomotion kind of hacks and techniques that they've added in so that even the people that are the most sensitive to VR sickness can play the game and still feel really good, because it's probably one of my favorite games, by the way. So pretty clever, doesn't add any development time. You just add a little rendering on the bottom. By the way, we're only seeing it in the bottom right because the game that this recording is only looking at the left eye rendering rather than the right, so obviously it would be different for the right eye. And this is for, Google Earth implemented this method called the grid world. So this is a way of every time you're moving positionally through a space, it constricts your vision so that you see the matrix that you're in, like the grid of the world that you're in, and it constricts the part of the Google Earth that you're actually flying through. That's typically how motion sickness really happens, is if your entire vision, everything that you're seeing is moving. And if you restrict that to just like a window, turns out you can move pretty quickly and pretty fast, and even for the most sensitive players, without really getting motion sick. So that's what they're doing here, and I guess it's a variation of the cockpit effect, if you think about it, because it gives you a grounded kind of sense of where you are. And this is a game called Lucid Trips, where you are in this like beautiful environment, and it's all about gliding and grabbing the world and floating. It's a way of actually, again, using the like physiological cues of like how you would be moving in the real world by grabbing the ground and flinging yourself, and visually like everything matches up with what your body is doing. So again, you don't need the full VR treadmill and running in the place for your body to feel like it's doing the right motion for you not to have motion sickness. So, I should also note, I should point out that, look, they also have streaks as well. When the player is moving quickly, you have these speed streaks. They have these dots that also come up that also are grounded to you and your position. So they've implemented multiple methods that are listed here, and at the end, it ends up being a very accessible game that people can play pretty well. So contrary to these things as well, it turns out you don't actually have to reinvent everything. So there's two games that I want to point out to, Onward and Pavlov, that are both first-person shooters, kind of like Call of Duty, or Counter-Strike is what this one looks like. they're like, we're not going to do teleport. We're not going to also put you in a cockpit either. We're just going to give you, a thumbstick, and you're just going to, move through the world, and hopefully, you won't barf from it. So what they did is that there's no acceleration in, with a stick. You can't just go halfway or full. As soon as you press on it, start moving in that direction. Turns out it still works. Perhaps VR has a self-selection element to it, so that the players that are playing VR, the people that would be motion sick, if they try VR and it doesn't really work well for them, they don't end up buying VR, and the people that are buying VR have stomachs that can handle it. Maybe there's a certain element to it, but turns out you could still do normal game mechanic locomotion, and it feels really good. So you can tell they're moving in a very fluid way, and like the hands are moving. VR gaming really is like at its nascent form now, but we're going to start seeing this kind of come up again and again. And the reason why I'm talking about locomotion so much is really that locomotion is what makes a VR experience, or a game at least, feel good. It's the part that creates like the good memories of the space, and for you to map out the places that you've been. Like all those nostalgic moments that you have with video games growing up is because you're moving through those spaces, and so it's an important problem to solve. Some future solutions that might be interesting to look at. So this is from Mayo Clinic, which they have a research division called the V-Motion, kind of spelled in a weird way. They are using something called a galvanic vestibular stimulation, and it's a way of stimulating your internal kind of like gyroscope and accelerometer, so that electrically, if the world is moving, they can simulate g-forces to the receptors in your head that would be feeling those g-forces. And so they have them in kind of like different directions. I don't know what the product actually looks like. This is just a rendering that they've put out there. But on the research side, GVS does exist, and we've seen some pretty interesting experiments over the last few decades of people trying it. I don't know if it's going to be implemented in future VR headsets. But it could be. You could imagine like wearing a pair of big headphones that have these stimulation sensors inside that would be simulating g-forces for you to feel. And perhaps with brain-computer interfaces, we might have better ways of also moving and not doing it. So some key takeaways. There's decades of research to build off of, and clearly there's been developers that have been like listening and integrating these things. There's hardware solution. The hardware solutions are, they could work, but probably are not the best decision moving forward, because VR already is expensive. A VR headset is right now $400, $500. If you're gonna fragment your user base with saying you need a VR headset and a VR treadmill, then it's like you're selling to 100 people at most. And there's a lot of great apps to learn from. And motion sickness is a big part of VR gamers because, I mentioned that earlier, that self-selection. Perhaps we need to worry about it even less than we think, because the gamers, or the people that are buying headsets today are not that prone to motion sickness. So the second big kind of problem, or one of the bigger challenges that is being solved in VR today, is visual clarity. And this has a lot to do with display technologies. And so we're going to talk a lot about the problems that exist and what research and science has been used to really solve these problems. All right. So visual clarity is really important for comfort, for immersion, and for the quality of experience. The initial Oculus developer kits actually had, let's look at this. This is the Oculus DK2. They literally were using a Samsung Galaxy Note 3. Like this is, when you disassemble the headset, they have the phone's panel in there. So they were just retrofitting phone displays into VR headsets. And it makes sense. That's not a bad thing per se, but it's, the reason why they did that is because it's just cheaper that way, and we're going to get into kind of what we need to actually be doing with future headsets for it to work more correctly for your eyes. Sorry, I'm just kind of jumbling back and forth in here. So some of the problems that come from retrofitting displays include low frame rate, because phones don't really need to run at 90 or 120 FPS, at least just as yet. If you're using an LCD panel, there's something called smearing, where if the pixels move fast enough, they don't actually refresh fast enough so that you have like almost like drift or lag within the pixels, and that will really cause motion sickness. There's a screen door effect, which is because you have the phone panel so close to your eyes, you actually see the sub-pixels and you feel like you're looking through a net, and I'll show you an example of that. And they are fixed focal displays, so you're only focusing at a very specific point. So this is the screen door effect. This is what, I think this is the Oculus DK1, and that's what it looked like. So you can just see exactly how the sub-pixels are actually composed of, and this is kind of what it looks like. That's the HTC Vive's configuration. That's the Oculus CV1, which is slightly less sharp, but at least has less screen door effect. And then this is some of the new headsets that are coming out that are just throwing more pixels. Let's just throw more pixels, and hopefully the screen door effect will go away. Turns out there's more clever ways of actually solving that. So this is Samsung, their new headset that just came out, called the Samsung Odyssey Plus, and they have this anti-screen door effect technology that is a way of like kind of blurring the sub-pixels together so that to your eye, they say it feels like a 1200 ppi display. Again, it takes advantage of like how your eyes work and how you can really still, you don't need to put 8K by 8K panels in these things and still feel like you're getting a sharp display. So some of the problems, the headsets today are kind of running closer to like 1200, 1400 p resolution. We're used to 4K, right? Like our TVs are 4K now. We're even starting to see 8K displays. We always want the better display technology. How do we add more pixels without blowing up our PCs and burning our melting our GPUs? So yeah, I mean 4K by 4K display. That's kind of at 120 FPS. That's like the next goal that we want to get to. One of the ways of doing it, again, goes to research and goes to actually how your eyes work. So this is something called FOVEATED rendering, and it requires having eye tracking inside of a headset for it to look at your eyes and understand where in the scene you're looking at. And what it takes advantage of is the fact that even though with our vision, when we're looking around, everything looks crisp and sharp in the real world, what you don't know is that only the place that you're actually looking at, like directly, if I'm looking at you, that 10 degrees of my vision is at the highest resolution that my brain is perceiving. And everything away from that actually, my eyes, my retina, does not really capture at the higher resolution. It's a way of like, it's kind of like compression. It's like hardware compression for your eyes, so it doesn't need to, be rendering everything at, I mean, your brain rendering is not probably the right terminology, but it basically takes advantage of that property, and using eye tracking, the computer can know what you're looking at, and everything beyond what you're looking at can drop off in resolution. So the periphery of your vision is like rendering at 20% of the resolution, and because your eyes already work that way, you don't perceive any difference in resolution. Doesn't matter if the panel itself is lower resolution at the periphery. Your eyes cannot tell the difference. And it really, I think it's up to 50% performance gains by having foveated rendering. So this is what we're going to start seeing this in in the next generation VR headsets as a very base minimum requirement to have. So on the developer side, you'll probably not need to do any math or anything special to integrate this. It'll be something that's going to be provided in the headset. Fixed focal displays. So this is the thing that I've been really interested in probably over the last 3 months is our VR headsets today, even though you have stereoscopy, two different images of the world that you're looking at, they're both flat videos, right? They're flat panels. And the way your vision actually works is that you have light coming into your eyes from all different directions. And if you close one eye, you can actually like change your focus from something that's close to something that's far, and you have like blurring of these things. I'll show you some examples. We've known how our brains perceive depth for quite some time. This is a stereograph from 1898, where photographers realized that if you take two pictures of the same scene from slightly different angles and actually look at them through a stereograph, you can have a real 3D image. So I don't know if you can do this from where you're sitting, but if you can cross your eyes and combine these two images into one, you can see a picture from 1898, 100 years ago in 3D, and they're actually incorporating like mirrors in this image as well, and so the mirrors also have depth. It's really like a brilliant photograph. So current headsets have stereoscopy, as in you can render two different images of the world and have depth perception. You have parallax, which start this. Parallax is the property that you get. You understand depth by just moving left and right and left and right. And you can tell exactly, you know, that this leaf is in front, where basically spatially everything is laid out just by moving left and right. It's actually, you can say it's a derivative of stereoscopy, but you're only seeing one camera at a time, like kind of like blinking your eyes left and right. And the last part of depth perception is depth of field, which VR headsets currently don't have. And this is that beautiful bokeh I'm talking about, right? Like, if you're focusing on that, on something far away, the things in the front are blurred. Like, this is very natural to how our eyes work. This is also how cameras work. And it's a property that is very hard to solve. And currently, VR headsets, they chose to put our focal distance at about 1.5 meters because it's kind of the healthy in-between zone for working on things that are close and working and like shooting things that are far without it causing really too much eye strain. So the fact that we don't have depth of field is this problem that occurs. It's called the vergence-accommodation problem. And it just leads to this visual discomfort. It leads to object and size like overestimation, and just general non-immersiveness. I don't know if I want to talk too much about the vergence accommodation problem. Yeah, the fact that we're very sensitive to focus. We're very sensitive to understanding where things are in the world in front of us and focusing on those things. And if you don't have true like light fields being projected into your eye, you don't really focus correctly. So here's some possible solutions as well, also coming from the research side, that VR headsets and AR headsets are starting to integrate. Oculus has something called the half-dome prototype, and it's a very focal display. So let's take a look at this. This is with a current, this is with Oculus CV1. This is the current VR headset. This is the new version that they've been showing, that they can actually move the panels closer and further based on, again, using eye tracking, looking at what you're looking at in the world and moving the panel to match the right focal distance that you're looking at, so that you can look at things that are up close, you can look at things that are far away, and you have real bokeh, you have real depth of field that gets generated. Light field displays. This is the cool thing that we keep hearing about. Light field is a big buzzword in VR. What does it mean? It basically means having a new type of display that doesn't just, I mean, let's look at this, right? This is just a very flat image that's being projected onto a wall that we're all looking at and focusing on this one depth. But a light field display would be projecting light in every direction, or maybe straight into your eye, but that your eyes can focus through the image itself. So if I have elements that are popping out of the screen, you'll be able to focus on the elements that are out here and in the middle and far back. Similar to how light in the real world works. We have light that's bouncing around the rooms, and our eyes are just kind of slicing through the light rays that are, you know, coming past my face. I don't know. Does this make sense, Peter? Hopefully. Stop me if I'm going too fast, or ask questions at the end, and I'm happy to come back to these. They're just if you're into these things, yeah, check out the podcast. Like we spend more time to really go in depth to these. So some of the solutions, like magically, they for a long time have said that if you don't solve this fixed focal problem, this accommodation problem, then you might even have like neurological or visual kind of damage that happens. And so their not so magical solution involves having two fixed focal screens, and based on where you're looking, they use one of the screens to focus. And it's not really a good solution. I think Oculus's half-dome prototype that actually has real continual focus is a much better solution. But we're starting to see a lot of companies trying to solve this. This is really going to be something that we'll have to fix. So some takeaways. Understanding how your eyes work turns out is really important if you want to work in this world. I mean, virtual reality is all about hijacking your brain, hijacking your eyes, and so to do that, you first need to understand how your eyes work here in the real world, understanding what optical illusions exist for your eyes, and perhaps taking advantage of those and seeing if you can get performance gains from that. So foveated rendering is one of those. Is actually the fact that your eyes don't render all the light that's coming into your eyes at the same resolution. That's something that you can really take advantage of. And again, with motion sickness, understanding how you can trick your brain into thinking that it's not actually fully moving, or the world is moving around you rather than you through it, can really help you build a much more well-designed and more accessible app for a lot of users. So thank you all for listening. I have my slides as a QR code that you can download, just so it's easier for everyone this way. And yeah, if you like any of the things that we talked about here, check out the podcast. It's on iTunes, it's on YouTube, Research VRcast. And then yeah, that's my Twitter as well. I like to tweet about these things. And yes, if you like to hear more about volumetric and photogrammetry, I have a talk at I think 4:30. So thank you. Yeah, if you have questions, happy to hear it. Please. Does multiplayer cause motion? Yeah, as far as I can remember, I think if you have motion blur, if you're looking left and right, it's the same property as the LCD displays kind of having the smearing of the pixels not like refreshing fast enough. It definitely can cause motion sickness, but yeah, you don't really need to add motion blur because you almost have like inherent motion blur by looking fast left and right. So yes, don't add motion blur. I don't think so. I mean, I think motion blur is something that's introduced because of cameras, as in, so films have motion blur because of the shutter speed that they're filming at, and having that match. I mean, when you're filming with a camera, you really need to know the limit of how fast you can move it without it looking juddery. Same with games, like in games you add motion blur to kind of simulate the cinematic element of a film. So I don't think real life is like that, as far as I know. Yes. 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 Oh, here, let's go back. This slide has a lot of them. So yeah, so the constant speed I think is probably one of the most important ones if you want to build kind of a traditional first-person shooter. Turns out you can do kind of like, as soon as you press the thumbstick forward, don't have any acceleration to the fastest speed. You could have, Onward has like normal movement and fast movement that you kind of, depending on where, I think on the thumb pad you're clicking, you go into, but having those visual streaks, like, let's go back to this, like this is a, damn, I don't like this app. This is a really effective one, and you see it a lot in a ton of games now, is the visual kind of like streaks, as well as the dots. So the snow that's actually coming down, I think, is like pretty clever at how they integrated it, so that you have these reference points of the world that you're going through. So the streaks are a really important element that they've added. Another one that I failed to mention here actually is that we can see it in lucid trips, is when you're moving, I think left and right, you can constrict your peripheral vision into kind of a much more of a tunnel vision. So you have a darkening of the peripheral vision. Again, it's so that you constrict how much you see, so that the window that the things are moving in is less problematic. So let's look at this video. It's kind of dark, but you can tell when they have some fast motion, kind of like the peripheral vision kind of constricts in a little bit. You don't really notice it, actually. That's also another property of your eyes, is your peripheral, so many things happen in your peripheral vision that you really don't notice. Turns out you kind of almost see black and white in your peripheral vision, so you don't even need to be rendering like the colors around the edges there. So yeah, there's really good elements. I think there's some good write-ups as well that you can pull up. I wanted to just talk about the main ones that some of these major apps have been using. And there's really, like, even though VR has been around for 2.5 years, like there's a lot of examples that you can pull from. But it just takes some time to like do your research and like know what's out there and learn what's working, because you just want to reduce that development time in iteration. But don't be afraid of movement. Like, that's one thing that I would tell developers, is that there's been some game developers that have just stuck to teleportation even after these 2 years, and man, gamers don't respond well to it. They really complain on Reddit about it, and when they have real motion, I mean, it makes sense, man. Like, it feels so much better when you're moving through a world than if you're teleporting through it. So it's important. Yeah. There was a question here. Yes. To help people that have motion sickness? Yeah. Totally. So one company is called Vivid Vision. I know we're running low on time. Vivid Vision is trying to solve lazy eye. People that have lazy eye syndrome, kind of using a VR headset and training the eyes, individual eyes, to look at a target and kind of training them to converge on the same spot. So there is a lot to using VR for like medical purposes, absolutely, and that's kind of what the medical side and the military side have been the two industries that have been funding VR research for the last few decades. So yeah, there's a lot to look into, and totally Googleable. Any final questions? Yes, last one. So I want to say yes, but I don't have real data to back that up. I think you can perhaps, it's called like growing your VR legs, kind of like how you grow your sea legs if you sail or you're on a boat for a while. So I think there's something to like repeated exposure, but I also know people that are even like VR developers that never have gotten over like fast motion games. And some games have been worse than others. And I'm lucky enough that I have like an iron stomach and I can endure the craziest experiences, but some people that really can't. So yeah, I encourage people to push along these things, because it ends up being a fun experience to fly and to move fast in VR. But you can run into problems with certain users, and you don't want to make your users barf. So yeah, you might be able to fix your motion sickness with VR, but don't quote me on whether it's actually there. I don't know, Peter, do you think? No?
One short tip, you can use ginger. Just keep it with ginger.
Yeah, that is one method. Ginger apparently can help you. If you get motion sick, ginger can help you alleviate the symptoms. And motion sickness, like, it's weird. It makes you want to. It's like horrible headache. You have to like lie down for a few hours sometimes. Like, I've had it happen once to me, and it was because of a 360 recording I did from a drone that was not stabilized, and I was editing the film in VR, and it was after an hour or two, I was just like, I need to get out of here. But most VR things are better than that. All right, thank you all for listening, and I'll see you guys next time. See you next year. Thank you.